Section 7.3 wraps up Chapter 7. We are looking at our last case for solving oblique triangles, and we're going to be using the law of cosines to do it. So far we focused on the law of sines. Now, just to recap, in Section 7.2 we listed out the 4 cases. In that first section of Chapter 7 we covered both case 1 and case 3. So we talked about when we know 2 angles, well, that means we really know that third angle, so we just find the third angle and then we use law of sines to find our remaining 2 sides. Or if we have 2 sides and the angle is included between the 2 sides, that side angle side, that is definitely congruent. We know we're going to have the same size and shape, and we use law of sines. We have skipped case 4, where if we know all 3 sides but we don't know an angle, because you can't use law of sines. You have to use law of cosines to do case 4 when we have side, side, side. And section 2 focused on still being able to use law of sines, but for that second case, that ambiguous case where we have to pay attention, we might have no triangle, just 1 triangle, or 2 triangles. If you have 1 triangle, you've always got to check to see if you have that second triangle that exists for law of sines with our ambiguous case. Alright, what if we have this 4th case where we don't have an angle, so we can't use law of sines? Well, we're going to use law of cosines. Now, something that you probably already kind of instinctively knew, but we hadn't talked about mathematically, in any triangle, the sum of the lengths of any 2 sides has to be greater than the length of that remaining side. Well, why? So let's think about this. If I tell you that I have a triangle and the side lengths of this triangle are 7 centimeters, 7 centimeters, and 15 centimeters. Well, that sounds like, okay, it's going to be isosceles. We've got 2 sides that are the same. We've got 7, 7, and then this other side is 15. But let's think about this realistically. If I have you guys stand, 2 people stand 15 feet apart on the floor, and I give these 2 people here a 7 foot long pole, and I want them to make a triangular shaped arch. Well, if this pole is 7 foot and this one is 7 foot, they're not going to meet. Those 2 are going to fall because they're too short. They're not going to meet in the middle. So anytime I have a triangle, the sum of the lengths of 2 of the sides has to be greater than that 3rd side. Otherwise, the triangle does not exist. So again, let's, if I was to say this is 12.4 centimeters, and I want this to be 6 centimeters, and this one to be 5.5 centimeters, that triangle does not exist because these 2 sides are not going to intersect up here. They're going to fall short, and they're not even going to meet. Okay, that is important information to hold on to. But let's talk about law of cosines. We're not going to go through and derive the law of cosines. We're just going to talk about the patterns. Now remember that you're going to be given the identity sheet on your exam. So you don't have to memorize these patterns. On your identity sheet, you're given law of sines, you're given those area formulas, you're also given law of cosines, and this Heron's area formula that we're going to talk about today. When you know the 3 side lengths of the triangle, instead of using this area formula, you're going to use Heron's formula. But you don't have to memorize these, you just have to understand how they work and know how to use them. Anytime you know all 3 sides, the length of the side, so a square, is equal to the sum of the squares of the other 2 sides less twice the product of those sides times the cosine of that angle. Right here is where that is put in words. According to the law of sines, the square of the side of a triangle is equal to the sum of the squares of the other 2 sides minus twice the product of those 2 sines and the cosine of the angle included between them. So if I have it set to a square, I'm using cosine of a. If I have it set to b square, I'm using cosine b. Same with c and c square. Whatever this angle is, that's the side it is equal to, and I'm using the other two side lengths in these pieces of the formula. Now, this might remind you, a square, b square, and c square might remind you of our Pythagorean theorem. So let's think about that. If c is 90 degrees, so our right angle, what's the cosine of that? Well, the cosine of 90 degrees is 0. So the cosine of c is 0. So if I'm using my law of cosines, I would have c squared equals a squared plus b squared minus 2ab, and the cosine of c is 0, so that whole term is 0, and I'm left with c squared equals a squared plus b squared, which is my Pythagorean theorem. And it's just a special case of the law of cosines. So the Pythagorean theorem is just a special case of the law of cosines. All right. Now, remember, because we're going to have to be using our inverse trig functions here, we need to be reminded that when we are working with our inverse trig functions, we restrict those functions to just two quadrants. So sine inverse is restricted to quadrants 4 and 1. We go from negative pi half to positive pi half. And cosine inverse is restricted to quadrants 1 and 2, going from 0 to pi. So that if I have a negative cosine value, I get an angle between 90, or pi half and pi, 90 degrees and 180 degrees. Negative cosine, I get an obtuse angle up here. Cosine inverse is negative, I have an obtuse angle. But over here, my obtuse angles live in quadrant 2. If I have a negative sine inverse value, I get an angle in quadrant 4. I'm not ever going to get a negative. I'm not ever going to get an obtuse angle. Because of the restrictions here, I will never have a return of an obtuse angle. So if I'm using law of sine and having to use sine inverse, it's never going to give me back an obtuse angle. It's never going to give me an angle in quadrant 2. Which means that if I'm concerned there may be an obtuse angle, I want to be using cosine inverse, because if it's obtuse, it's going to show up when I'm using cosine inverse. Alright, this next bit is a nice chart to organize our thinking. It gives all 4 of our cases and some steps to follow so that you know what to do when. Keep in mind your restrictions for your inverse function values. Our first case is when I know one side and 2 angles. Doesn't matter what order they're in, because actually if I know 2 angles, I know that third. That's my first step. Find that remaining angle using that angle sum formula, which simply means that if I add up the 3 angles, I get 180 degrees. And then I find the remaining sides, because I only know one side. I find the other 2 sides using the law of sines. That's what I do if I'm presented with a triangle that gives me case 1. 2 angles, one side is known. Alright, case 2 is my ambiguous case, right? Case 2 is my ambiguous case. Well, if it's the ambiguous case, I might have no triangle, 1 triangle, or 2 triangles, and I need to make sure I figure that out. I find an angle using the law of sines, and there's no choice here. There's only one other piece of information, so I find that angle. And then the remaining angle is found using that angle sum formula. And the last side is found using the law of sines. Now, since it's the ambiguous case, if I work all the way through with one triangle, I've got to check for the second triangle. I've got to check. If I have one triangle, I have to check for that second triangle and find out if it exists or not. Now, case 3 also has two sides and one angle, but the angle is included this time. The included angle, included between the two sides, so it is not ambiguous. But if we're not careful, we can end up making it look like it's ambiguous. So I want to make sure that when I'm working through this, that I follow these instructions. Find the third side using the law of cosines. Well, why would I do that? Well, I'm going to do that because I don't have a pair of information. If I have side angle side, I don't know the side length opposite this angle, and I don't have a way of finding one of the two other angles. So I'm going to start with the law of cosines. This is that third case. I said that we'd already worked with this, but we worked with it with area. We didn't work on it with law of sines. I'm sorry, that was misspoken. I want to start with the smaller of the two remaining angles using law of sines. Now, the smaller part is important. Remember that we said if I'm doing sine inverse, it will never give me an obtuse angle. So if I'm starting with the smaller of the two, I know it's not obtuse. I know that that smaller angle is acute. So when I use law of sines and I have to do sine inverse, it's going to land in quadrant 1 no matter what. I don't have to worry about missing an obtuse angle. And then my third angle, because I was given an angle, I found a smaller angle. When I use that angle sum formula to find the third angle, if there's an obtuse angle, it will be this one, and it will definitely show up. My fourth case we're going to look at today, that's when I know those three sides. I'm going to start with the largest angle here because I'm going to start with the law of cosines. And the law of cosines, cosine inverse, will give me an obtuse angle if there is one. If there is an obtuse angle, I'm going to find it first. And if there's not an obtuse angle, you're going to know that because the largest angle will have been found and it won't show up as obtuse. So since we had to use law of cosines, we know whether or not that angle is obtuse. And now I have a side and its angle that is opposite, so I can find either one of the remaining angles using law of sines. Why wouldn't I do law of cosine again? Well, law of cosines is more work. You're going to see that in a minute. And that third angle is always found using the angle sum formula because it's easiest to subtract what you got from 180. Okay, we're going to jump right in with an application problem. So when we do our sketch, we're going to be sketching the situation that we've been given. Two boats leave a harbor at the same time, traveling on courses that make an angle between them of 82 degrees 20 minutes. Alright, so we've got the harbor here. One boat heads off this way, the other boat heads off this way. This angle in between is 82 degrees 20 minutes, or 82 1/3 degrees. 20 out of 60 minutes. When the slower boat has traveled 62.5 kilometers, the faster one has traveled 79.4 kilometers. So we got a slow boat and a fast boat. At that time, what is the distance between the two boats? So that's my question. Now if I want to label these, let's make our boats A and B. Our harbor will be at C, so we're looking for side length C. We've got side angle side. We can't use law of sines because we don't know both pieces of information about any one thing, like we don't have both values for C or A or B. We're going to have to use law of cosines. Now, the law of cosines value that we pick is going to be based on what I know. Well, if C squared, for my law of cosines, C squared equals A squared plus B squared minus 2AB cosine C. I want to solve for C. So I'm going to take the square root of both sides. Now, when I take the square root, I have to consider plus or minus, except we're talking distance, so we know that this is going to be positive. So A is 79.4, B is 62.5, and then I have to subtract 2 times the product of those lengths with cosine of 82 1/3 degrees. This is basically a calculator math problem, right? I've got to make sure that I use order of operations correctly. I want to find everything under here before I take the square root. I want to square this, subtract this product. When I'm done, I want to keep 3 significant digits because that's what I was given in the problem. So I discovered that the boats are about 94.3 kilometers apart. 94.3 kilometers apart. So when I plug this into my calculator, I will do, I've got degrees in degree mode, so that checks. So I've got 79.4 squared plus 62.5 squared minus, and then I can just make sure I'm showing that I'm multiplying all of these. 2 times 79.4 times 62.5 cosine, and then it opens up my cosine argument, parentheses 82 plus 1/3, 1 divided by 3. I'm going to close that. That is the value underneath my square root. So I'm going to do second square for my square root and just do that second answer combination to bring that up, and it rounds to 94.3 kilometers. Alright, so let's look at our next example. Remember that it's important to draw an accurate sketch. If you don't start with an accurate sketch, you don't know what you're looking at and what you're looking for. So I really want to encourage you to take a second, pause the video, draw your sketch, and then start the video and compare it to mine. So we have a surveyor trying to find the distance between points A and B, and she can't just walk across the lake. So she finds the value of this angle and the distances from this common point to each value. So side A is 423 meters, side B is 259 meters. The angle between is 132 degrees and 40 minutes. And what I'm looking for, what I'm trying to solve for, is the distance across the lake, this side C. This ends up being the same calculation that we just did, law of cosines, but obviously with new values. When you plug it into your calculator, it should get you something like that. I've obviously rounded off my decimals, which is approximately 628 meters. Meters, make sure you use the correct units. I rounded to 3 significant digits because that was what I was given in the problem. Alright. Now this one is not an application problem, but we're going to need to do our sketch for our triangle. There's my generic triangle ABC. B is 73.5 degrees, side A 28.2 feet, side C 46.7 feet, side angle side. I can't use law of sines. There's no way to use law of sines, so I have to start with law of cosines. Since I know angle B, my first step is going to be to solve for side B, which means I've got a squared plus c squared minus 2ac cosine b. I'm not going to take the time to write down my values. I encourage you to do so when you plug that into your calculator. You should end up with a side length for side B of about 47.2 feet, which lets me know that angle B is the largest angle, because this side B is the longest side. So I know that side C is going to be a little smaller than angle C is going to be a little smaller than angle B. Angle A is going to be the smallest angle. Those are things that I anticipate. Which of these two angles do I find next? Well, in general, I'm going to be using law of sines because I know paired off piece of information now. I know side B and angle B. Since I'm going to be using law of sines, in general, I start with the smaller angle first when I'm using law of sines. And I know C is going to be smaller. So side C over the sine, angle C is what I'm finding. I'm looking for side C. Let's fix that. Looking for angle C. I know side C. I just misspoke again. There we go. So we've got the side length over the angle. We've got our side length over sine of angle B. Oh, that's not my smaller one. That's my larger one. Guys, I got distracted all over the place. Let's just fix it. Angle A is smaller. So we're doing angle A over side A because that's my shortest side. Now we're talking. When you plug that in, you should get a sine function value for A of about 0.57285, which is a legitimate sine function value. When I do sine inverse, it's going to work. So angle A is going to be sine inverse of that value, not rounding off in my calculator, so that when I get angle A, it should come out to be about 34.9 degrees. And then my final step is going to be to find that third angle measure. In the third angle measure, I always use the angle sum formula. I start with my 180 and I subtract out the two angles I know to get my third angle. Alright, let's look at our third example. This one we're going to be doing side, side, side. So we start with our generic sketch for side, side, side. Let's do A, B, C. Side A is 25.4, side B is 42.8, and side C is 59.3. So what do I know? Well, I know that angle C is my largest angle, and I know that angle A is my smallest angle. Which one do I start with? Well, since I don't know an angle at all, I'm going to have to use law of cosines. Will law of cosines give me an obtuse angle? Cosine inverse is restricted to quadrants 1 and 2. Yep, it will return an obtuse angle. So we're going to start with our largest angle first when we do law of cosines. Well, our largest angle is opposite the longest side. So I'm going to start with c squared equals a squared plus b squared minus 2ab cosine c. And this angle c is what I'm going to be looking for. So I'm going to end up rearranging terms for my function. I want to get cosine c on one side by itself. And I can rearrange those terms kind of however I want to. If I move this over to make it positive, I would have 2ab cosine c equals, and then I would have a squared plus b squared minus c squared, because I would subtract that c squared over to the other side. And then I need to divide by 2ab, so that I have cosine of c is equal to all of that. And then once I find cosine of c, I'll have to do cosine inverse to find the value for angle c. Again, I do my sketch because I want to make sure that I'm careful about getting the values in the correct spot. So 25.4 squared plus 42.8 squared minus 59.3 square over 2 times a and b when you do all of that, you should get a negative cosine function value, which tells me that, yeah, I'm going to have an obtuse angle. It's a good thing I started with cosine inverse for this angle, because it's going to give me that obtuse angle. If I do cosine inverse of that value, now I've rounded this off to write it down, but you're going to be not rounding it off in your calculator and using it. You should get 118.6 degrees. That's my first angle. I have 2 more angles to figure out. I don't want to have to do law of cosines again because it's more work. So I'm going to switch over and I'm going to do law of sine for the next angle. So I found my obtuse angle, angle C. Found that one. If I go for my smaller angle is going to be angle A. So let's just do that next. Let's do sine of A over 25.4 equals sine of angle C, 118.6 over the length of side C, 59.3. You guys, we've been doing sine inverse for a while now, law of sine. So I figure out that angle A is 22.1 degrees. Now that I know angle A and angle C, I can just use my angle sum formula to find angle B. And I come up with 39.3 degrees for angle B, and I've solved the triangle. Alright, one more example for law of cosines, and then we're going to switch and we're going to talk very quickly. Heron's formula for area is super simple. We'll work through it after we talk about this application problem. So a roof truss. If you've ever seen them building a house, you'll notice that they build these triangles that go up to support the roof on top of the upper story of the house, and they typically build those down below and then they put them all up. We want to find the value for angle C to the nearest degree for this roof truss. Theoretically, I guess if you know the lengths of your sides, everything should be the same, right? But we want to check and make sure that everything is at the same angle. I know my 3 side lengths, so I'm going to have to use law of cosines to find the angle. We're finding angle C, so we would start here. Rearrange our terms. We just rearranged our terms one way. If you want to rearrange them another way, where I would subtract a square and b square, I would end up with c square minus a square minus b square, and then I would need to divide by this coefficient, negative 2ab. That's another way to solve for cosine of c. So this is going to give me an equivalent answer to how I rearranged the terms last time. Whichever way you go, you should get a cosine function value for c 0.5757. That would start with negative 76 over negative 132, or a positive 76 over a positive 132, depending on which way you moved your terms. But once you get your cosine function value, you use cosine inverse. We're only going to 2. We're going to keep it just not, we're going to round it to no decimal places. C should be about 55 degrees. Now, if you want to find angle B for this same truss, you don't have to go back to law of cosines. You could use law of sines. Because now that we know angle C and side C, I can use law of sines to find the measure of angle B. You can choose to use law of sines, or you could practice your law of cosine again, which I would encourage you to do. No matter which way you do it, you should get a value for angle B of 33 degrees. Okay, we're going to take the rest of our time and we are going to look at Heron's formula, which is our other triangle area formula. We use Heron's formula when we know the 3 sides. Heron's formula involves a length S, which is our semi-perimeter. Perimeter is distance around any shape. Semi-perimeter is halfway around. So if I add up the lengths of the sides and take half of that, that's my semi-perimeter. Now, Heron was Heron of Alexandria. Just a quick history note. Heron of Alexandria, Egypt. He lived about AD 75, and he is the one credited with this particular triangle area formula. To find the area of a triangle using Heron's formula, you have to find that semi-perimeter first, and then you take the square root of the product of the semi-perimeter multiplied by the difference between the semi-perimeter and each side length. Okay, we're going to do 2 examples, and these are nice application examples. The distance as the crow flies, which just means straight. The distance as the crow flies from Chicago to St. Louis is 262 miles. St. Louis to New Orleans is 599 miles. New Orleans to Chicago is 834 miles. What is the area of that triangular region between those 3 cities? Well, okay, so if we want to do a rough sketch, we've got Chicago up here. St. Louis is kind of this direction, and New Orleans is down here, and they form a triangle. They form a triangle in the 3. Chicago to St. Louis is 262 miles. St. Louis to New Orleans is 599 miles. New Orleans to Chicago is 834 miles, and I want to know the area of this triangle. Well, I don't have any angles, so I would have to use law of cosine and do a lot of work to come up with the information I need to use the last set of area formulas that I used. So we're just going to use Heron's formula. The first thing I need is my semi-perimeter. The semi-perimeter, that side length, is always going to be more than each of the 3 sides. So there's my semi-perimeter S. And I know this is always going to be larger than those 3 sides because I need to, when I subtract each of the sides from that semi-perimeter, I should get a positive value. So my area formula, Heron's area formula, it's semi-perimeter, and then I do semi-perimeter minus side A, semi-perimeter minus side B, semi-perimeter minus side C. So I multiply the semi-perimeter, and then I subtract. So 847.5 minus 262 is going to give me 585.5. 847.5 minus 834 is 13.5. And 847.5 minus 599 is going to be 248.5. Now, each of these values, again, needs to be positive. If it's not positive, you messed up something with your semi-perimeter. You need to go back and look. In your calculator, find this product, multiply that all out. Take the square root of that value. Area is square units, so we've got about 40,800 square miles. How did I end up rounding to that point? Notice that I've got 3 significant digits here, so I've got 3 significant digits here. One more challenge, pause the video, set this up on your own, and then come back to see if yours matches mine. We're finding the area in this triangular region. Notice it tells us to ignore the curvature of the earth. We don't need to add in. Actually, triangles on a curve, you end up with angles that are a little bit more than 180. It's an interesting calculus problem, but we are keeping it flat. We're ignoring that curvature of the earth. When you work this out, your semi-perimeter should come out to be 2,604.5 miles. Again, your semi-perimeter will always be longer than each of your sides, so that when you find the difference between the semi-perimeter and each of those sides, it's going to be a positive value. When you use your Heron's area formula here, you're going to get this, 401,664, but if we keep it to significant digits, we record that as 401,700 miles square. Again, units are important. Make sure you use the correct units.